We're next going to talk about an algorithm that also takes O of log n time, called Euclid's algorithm. Let's suppose we have two integers, let's say 50 and 15. We say that the greatest common divisor of two integers, which we're going to denote as GCD, is the largest integer that divides both numbers. So in this example, we need to find the largest number that divides both 50 and 15. And in this case, we find that the GCD of 50 and 15 is 5. So how do we actually know that the GCD of 50 and 15 is 5? Well, one simple approach is let's take a look at the numbers that actually divide both 50 and 15. So let's start by looking at the numbers that divide 50. So we have 1, 2, 5, 10, 25, and 50. As far as I know, those are the only ones that divide 50 evenly. Now let's take a look at the numbers that divide 15. Well, we have 1, 3, 5, and 15. So all we have to do here is take a look at these two lists and just find the number that exists in both, the largest number that exists in both these lists. Because by definition, that would be the greatest common divisor. Well, if we look at these two lists, the largest number that's common to both of them is 5. I cannot find a larger number in either list that divides both 50 and 15. Therefore, the greatest common divisor has to be 5. There is another way to compute the GCD. And the way we do this is we would compute remainders until we get a 0. And then the last non-zero remainder would actually be our greatest common divisor. So let's take a look at some code that does this. So this is the actual implementation of Euclid's algorithm. So here we have m and n, so we're trying to get the greatest common divisor of m and n, and here we're going to assume that m is greater than or equal to n. If not, then we can just flip-flop m and n and we're good. So as long as n is not equal to 0, we'll compute the remainder of m divided by m. So that's what we're doing on this line right here. So we'll get our remainder, and then now we're going to change the values of m and n. So m will become n, and n will become that remainder. And we just keep repeating this until n becomes 0. And then when we're finally done, whenever n does become 0, m is going to be that last non-zero remainder. So we're going to return this value as our answer. Now, you might think this seems like a very odd algorithm, and you may not be so sure if it works or not. Well, we're not going to do a formal proof of correctness, but we will use this algorithm with our example of 50 and 15 and show that it does give us 5. So if we're going to get the GCD of 50 and 15, here m is going to be 50 and n is going to be 15. So in this case, n is not 0, so 15 is not 0, so we'll go into our loop. So if we're going to compute the remainder, well, the remainder of 50 and 15 is going to be 5. If you don't believe me, try to divide 50 by 15, and you'll see the remainder is 5. So now we're going to reassign the values of m and n. So m is going to become 15, and n is going to become 5. So we're going to go back into our loop. 5 is not 0, so we would go into the loop. We'll compute the remainder again. So in this case, the remainder of 5 and 15 would be 0. So that means that m becomes 5 and n becomes 0. And then the next time we go to the loop, we see that, well, 0 is 0, so n is 0. So we would get out of the loop and we would return m, which in this case is 5, which is the GCD of 50 and 15. So what's the running time of Euclid's algorithm? Well, let's take a look at the body of our loop first. And we find that it takes constant time because we're just computing the remainder, we do some assignments, and then the stuff that comes before and after loop are also constant time. So the running time of this algorithm is going to depend on the number of iterations of our while loop. And what we find is that after 2 iterations, the remainder is at most half of its original value. And then if we do another 2 iterations, the remainder is going to be half of that value, and so forth. Now you might think that, is that really true? Well, let's show it so that you're actually convinced. So we want to show that if m is greater than n, then m mod n, or the remainder of m divided by n, is less than m over 2. If we can show this, then we can figure out the number of iterations of our while loop. Now we have two cases to consider here, and it depends on the value of n. So let's just suppose that n is less than or equal to m over 2. Now this one's pretty easy to show because we know that m mod n has to be less than n. It has to be a value that's between 0 and n minus 1. But we're assuming that n is less than or equal to m over 2. So if n mod n is less than n, and n is less than or equal to m over 2, then n mod n must be strictly less than m over 2. So that part is fine. Now let's consider a second case, where n is strictly greater than m over 2. So what's going to happen is when we divide m by n, the remainder is going to be m minus n. And that has to be less than m over 2. There's just no way around it. It has to be strictly less than m over 2 because since n is already more than m over 2, when we subtract n from m, that result has to be less than m over 2. So that means that the m mod n has to be less than m over 2. So we're good there. So we've shown this. So after 2 iterations, the remainder has to be half of the original value, or m over 2. So what that means is we have 2 log n iterations. Now the 2 part is removed in the O notation, so this turns out to be O of log n iterations. Therefore, the total running time of the algorithm is going to be O of log n.